We're starting with Unit 8, Work, Power, and Energy. This lesson will be over both work and power. So when is work actually work? Okay, in physics, work is done when these two things happen. Okay, force is applied to an object and that object is moving through a distance in that same direction as the force is being applied. So some truths about work is that it's always a positive number. We measure work with the unit joules with a capital J, and work is not done if the object does not move.
So take a look at that picture in the upper right-hand corner, all right? What Ms. Case said, first you have to have a force applied. There's your yellow arrow. It's applied to that blue object, and the object moves as a result of the force, all right? So that object moves in that same direction. Notice the direction of those arrows are the same. Those two things have to be true every time to be considered work in physics. So look at the picture below, right? You have two examples there. You have holding a box, and you have raising that box. So when I hold the box, it requires me to exert effort, but not do work. Because if I'm just holding the box is not moved through a distance in the same direction as the force. So it doesn't meet the second requirement, so it's not considered to be work. When I raise that box that I am holding, now I'm doing work because I'm exerting a force upward and the box is moving upward. So make sure that you say to yourself for every example, as Ms. Case will go through a couple in a minute, for every example of potential work, make sure that both parts 1 and 2 of the requirements are met. Then we are considered to be doing work according to our definition in physics.
All right, so on these, you need to decide if work is being done or if it is not being done. So we're just going to go over the first two here. Pushing a chair across the floor. So again, which direction is our force being applied, and is that object going in that direction? So a chair being pushed, so if our force is going forward, that chair is also moving forward. So work is being done here. Lying in bed. When you're laying in bed, your force is going down, right? You're pushing down on the bed. But is the bed moving down? Nope. So force is not being, our work is not being done here. When we are calculating work equation is W equals F times D, or work equals force times distance. This equation setup is just like the many others that we have seen. So rearranging those variables will look very similar. So isolate those variables in order to come up with the other two equations. Please make sure that you're making note that work is measured in joules, or a capital J. Force is still being measured in newtons with a capital N here, and distance is measured in meters, or a lowercase m.
All righty, and let us jump over to our jam to take a look at some example problems here. So we have 3, I think, examples for work. And as Ms. Kay said, we're going to do some rearrangements of our variables as we go through with these different equations to make sure that we are able to take a look at each of those examples. So if we read through our first problem here, all right, if I pull on a cart with 15 newtons, all right, of force, it moves 3 meters, all right? And the question is, how much work have I done? So the first thing you need to ask yourself when you have a problem that's asking for work, right? That's my unknown. And why wouldn't there be a technological difficulty at this moment? Because it's not Ms. LaForte's computer if there's not one. So, all right. So if work is our question mark, all right. If work is our question mark, where's my question mark? W equals question mark. I need to ask myself, is work actually being done? So is a force applied? Yes, it says 15 newtons of force. And does the object move in that same direction? it moves 3 meters. Yes and yes. So that means I am going to calculate a numerical value for work. All right. So let's label or identify those other things that we have there. We have force of 15 newtons. And we have a distance of 3 meters. All right, so that is our given information, and we can label that underneath here as well. F and D. Right. As Ms. Case just mentioned from our previous slide, work is equal to F times D. All right, so there is our, capital W. All right, so there is our equation. And then you should know the rest here. So you're going to substitute and you are going to solve as you are working through this. And you are going to get that information plugged in. So I'm going to write that out as well. Newtons. Times my 3 meters. Right, and if I do this, that would be helpful. It's just all technological difficulties, always. All right. Hopefully you got the same answer that Ms. Laporte did. Hopefully you put the right units with your answer because we're solving for work. So I'm going to have 45 as my numerical answer, and our unit should be joules with a capital J. All right. Hopefully no issues with that. Same kind of process we've done many times with our guess method. In case you want to talk through the second one here.
Sure. So we say if I pull on a box for 2 minutes with 150 newtons of force, but the box doesn't move, how much work have I done? So first we're going to identify the important parts that we have here. So we've got time and we have 150 newtons, which tells us our force. But we do not have here is direction. Okay, because it says it doesn't move. So it's moving how far? It's moving 0 meters essentially. Okay. All right. So now when we go through and we do our math or any of this, our given, we're trying to find how much work are we doing. Remember, work is your force times your distance. So your force is 150 newtons. Your distance is 0 meters. So your W is your question mark. All right, so now we substitute and we solve. So we have 150 newtons times 0 meters. 150 times 0 gives you 0. And our unit for work is joules. So here we notice that I am not doing any work. Okay, I might be putting in a lot of effort, but I'm not doing any work.
Excellent. All righty, and for your last example here, all right, let's take a look at what information we are given for our third and final example. If I have done 200 joules of work while pulling a box with a force of 20 newtons, how far did I pull the box? Okay. All right, so I've underlined some information here. It says 200 joules of work, so obviously that is my W. It says I pulled the box with a force of 20 newtons, so that is my force. And this time it's asking me how far did I pull the box, okay? So this time we're gonna look for distance, all right? I'm just going to, for those of you that like to write them out, I'm gonna put them down in our givens. Force equals 20 newtons. Unknown, this time is distance. So we're gonna have to rearrange that equation, all right? So our original equation, right? Our original equation said, no, we got it. Our original equation said work equals F times D, all right? But I want to solve for D because I don't have it. So I'm going to isolate this variable using a case term And I'm going to keep D here, and I'm going to move force to the other side. In order to do that, I have to divide both sides by F. In other words, my equation is going to be D equals work divided by force. All right, so this is what I'm going to use with my given information. So I'm going to take that work, which was 200 joules, and I'm going to divide it by my force, which is 20 newtons. Oops, terrible. It's like an 8. All right. And so when I do that, I should end up with a distance, right? My math is good. A distance of 10 meters, right? My distance unit is meters. So again, make sure that you are rearranging your equation, our 3 variable equations, so that you have all 3 equations for you. But remember that even if you don't remember what that rearranged equation is, you can still figure it out just by rearranging your variables during your work. Okay.
All right, so now we are going to take a look at power. Power is the rate at which work is being done. So this is given the same amount of work done, the faster that you do the work, the more power is generated. Okay, so this is where time is coming into play. And our power equation is P equals W divided by T. So P is for power, and we measure power in watts. W stands for work, and we're still measuring that with our J, our capital J for joules. And now we're adding in time. So time is our T, and we are measuring that in seconds.
All right, one thing you need to make sure you are very careful with is in equations, we use variables. Just like in math, you use variables like x's and y's. In an equation, the P, the W, and the T stand for the word of the variable. P for power, W for work, T for time. Each of those variables is represented by a number with a unit, all right? And these letters over here, capital W for watts, capital J for joules, and lowercase s for seconds, are the abbreviations for the units. So it's very important that you make note that difference so that you are not mixing that up, okay? So when we talk about things being powerful, what we are really meaning is they can do the same amount of work as something else, but they can do it faster, right? And that's the reason why we use machines to do a lot of our work, is because they can do the same work we would do, but they can do it way quicker, all right? And that's what we're gonna look at here. These first 2 examples that you have here, you are going to answer those questions, and then we're gonna discuss those in class. So make sure that you take a look at what it's asking to see if you can figure out which of these objects or events are going to have more power. And then in your notes, make sure that you write your defense, if you will, of your answer, why you said what you said. We are going to work through the last problem here, and I'm going to let Ms. Case talk you through it. I think I might have fixed this situation, but you never know.
All right, so the question is, who had the most power? So Kyle pushed a cart 11 meters in 6 seconds with 18 newtons of force. Adam, who pushed the cart 9 meters in 9 seconds with 15 newtons of force. Or Rink, who pushed the cart 15 meters in 5 seconds with 20 newtons of force. So first we need to go through and underline and identify all of our important information here and probably separate them by the person. Okay, so just like Ms. Laporte is doing here, we've got 11 meters is our distance with meters, 6 seconds is our time, and our force is 18 newtons, and that's for Kyle. Now we have Adam. He has 9 meters, 9 seconds, and 15 newtons. So 9 meters is our distance, 9 seconds is our time, 15 newtons is our force. Rink pushed the cart 15 meters is our distance, 5 seconds is our time, and 20 newtons is our force. So we need to start by solving for each one of their power. Because that's what our question is. That's our unknown is our power. So first, let's look at our givens for Kyle. We've got 11 meters, 6 seconds, and 18 newtons.
Got a color code case.
Yeah.
Can't be going off the reservation here.
All right, and then we have Adam. His givens are 9 meters. For distance, our time, 9 seconds. And our force is 15 newtons. And then we have Rink. Distance is 15 meters. Time is 5 seconds. And force is 20 newtons. So all of these are looking for power. And your next step should be writing down your equation for power. And when you were given that equation in the notes here, P equals W divided by T. However, we don't have the W here. So we need to think back to what we taught you in the beginning of this unit, that W is actually equal to our force times our distance. And that's what we'll be using as our numerator. All right, so that's the formula we will be using for all 3 of these power problems.
So what you're going to do right now is you are going to solve for Kyle's power using this equation. Then you're going to solve for Adam's using this equation. And then you're going to solve for Rink using this equation. And then you are going to answer your question in your Edpuzzle.